Good afternoon. Welcome back to the online seminar series Machine Learning Needs Mathematical Optimization. We have the pleasure today of having Stefan Wagner from the Stanford Graduate School of Business. He's an assistant professor of operations research, information and technology. His work is at the intersection of statistics, economics, and decision making, and he applies the latest techniques in machine learning to these fields. He has published in renowned journals such as Annals of Statistics, Econometrica, Journal of the American Statistical Association, Journal of Operations Research and Management Science. He is serving as an associate editor for Biometrica, Journal of the American Statistical Association and Journal of the Royal Statistical Society. And he has also been very successful with fundraising, for instance, from the NSF. Me being Spanish, I have to point out that we are also thankful to Stefan for his contribution to TEST as a discussant. TEST is the statistical journal from the Spanish Statistics and Operations Research Society. So we are very pleased to have you today. The floor is yours, and for the audience, if you have questions, please put them on the chat and I will read them to Stefan. Thank you again.
Thanks a lot for the introduction and for the invitation. It's a pleasure to be here. So today I want to talk about large sample theory for sequential experiments, or equivalently for stochastic bandits. So just as a little bit of context, by now randomized trials are widely used in many different areas. I think it's been a long time that randomized trials have been widely used in medicine. It's more recent that there's such regular use of randomized trials across the board, ranging from development economics to business applications. And randomized trials have pros and cons, right? The pro is that they let you learn about the relative merits of a number of different actions in a very transparent and rigorous way. But the downside is that they come at a high cost. You have to send a potentially large number of people to suboptimal actions. So just to illustrate this phenomenon, here's one motivating example from a vaccine trial. I promise I wrote this example a little more than a year ago, before everyone was thinking about vaccines all the time. So in this example, imagine choosing between three candidate vaccines. We have 3,000 people we can assign to treatment in this trial. And in a randomized trial, we might send 1,000 people to each of the three candidate vaccines. And we're trying to find the best out of the three vaccines using a randomized trial. And you could do this. And here you see kind of over the 1,000 people enrolled in the trial. Let's say you're measuring an outcome you can assess quickly, like did you have an immune reaction to the vaccine? And here, vaccines number 1 and 2 are doing quite well. You're getting above 80% of people are having an immune reaction to it. Vaccine number 3 is less good. You're getting somewhere between 60 and 70% immune response. So running this randomized trial would have been very interesting, right? You would have learned that arms 1 and 2 are better than 3. But at the same time, you might also notice that, look, after enrolling 200 people in the trial, you could also already tell, or 200 people to each arm, you could already tell that arm 3 wasn't very good. Arms 1 and 2 were where it's at. And once you had noticed this, maybe you should have just stopped experimenting in arm 3 already, moved all your samples to arms 1 and 2, so you can focus power on distinguishing these two. This would give you more power to actually figure out which arm is best, which you weren't able to do here. And it would also just mean that you assign fewer study participants to arm 3, which just was less effective vaccine protection. So sequential experiments, or bandits, are an answer to this challenge. sequential experiments are like traditional randomized trials, except that you can change randomization probabilities on the fly in response to past observations. And what's the purpose of this kind of changing randomization probabilities over time? There could be a number. It could be to avoid taking kind of poor actions. Just if you want to avoid unnecessarily harming people in the study. Once you notice an action is bad, you don't want to send people to those actions anymore. Or you could use this for concentrating statistical power on the most promising arms once you've already identified that some other arms are less good. And in this setup, the fundamental tension is between kind of exploration and exploiting knowledge you already have. So the more you randomize your actions, the more you can kind of learn about everything that's going on. But then once you've learned something, you don't want to take bad actions anymore. You want to exploit that knowledge going forward. So this is the tension. And this is obviously kind of a widely used formalism. And it's been studied quite a bit in the literature. That being said, I mean, of course, there's a huge number of application areas where you could deploy sequential experiments, and the challenges in different application areas look a little bit different. So far, most successful applications of sequential experiments have been in automated decision making. For example, one thing that comes up a lot is something around website optimization. You want to figure out what kind of text should you have to maximize engagement. You'll have the likes of Google running thousands or more experiments in parallel, trying to kind of optimize every aspect of a website experience. You're trying so many different things. You're running these automated experiments. Sequential experiments are a perfect fit for this, right? Because you can quickly try a lot of things and discard less promising alternatives on the fly. Similar considerations come up in pricing. What's distinctive about these problem settings is that you're running kind of a bunch of experiments at the same time with fairly limited human oversight. So when kind of the theory community has looked at these application areas, what's a natural question to ask? Well, it's something like, I have this sequential experiment. How can I guarantee that kind of regardless of what nature throws at me, regardless of the sample size, I can always get robust worst case guarantees that kind of can give me peace of mind in deploying these methods. So, and this is in fact what the theory community has looked at. If you look at formal literature on sequential experiments or bandits, there's a lot of work on finite sample, robust upper bounds on regret. So this is helpful. But more recently, there's been another class of application areas where people have also been considering the use of sequential experiments. And this is in these high stakes, closely monitored settings that just look very different from these automated website optimization problems. For example, recently there was one paper that considered using sequential experiments in assigning refugees to jobs training programs in Jordan. And so this is not going to be this kind of application where you're running 1,000 experiments in parallel and no one has time to even look at what's going on. Quite to the opposite, right? This is going to be something where you're going to have a number of researchers who are closely monitoring everything that's going on in the experiment. And you just want to make sure that everything is going just right. And so this is qualitatively, it's a pretty different application. Quantitatively also, you might be interested in different guarantees. You might be less interested in these kind of robust worst case guarantees, kind of nothing could go wrong. What you're interested in these kind of very nuanced, instance specific distributional results on performance. You might want to ask, if one job training program is a little bit better than another one, then what could kind of the fine-grained behavior of the sequential experiment look like Can you run through counterfactuals of how the experiments might play out? This is the kind of guarantee one would want. So anyways, and these guarantees generally don't follow from standard worst case results on bandits. And so that's kind of what I want to think about in this talk. So anyways, just to be concrete about what the problem setting is, so we're going to be looking at sequential experiments in a multi-arm model where we have I going from 1 up to n decision points. At each decision point, you have an agent who takes an action, observes the reward, and then based on this action and reward, they can update their beliefs and use those beliefs going forward. The key modeling assumption is that conditionally on the action you take, your reward yi is drawn from a distribution PAI that depends on the action, but it's independent from everything else, right? So the past information can affect which actions you take, but won't affect your distribution outcomes conditional on action. And I'm going to call mu k the mean of the kth reward distribution. So this is a setup, and then what are some questions you might want to ask here? Well, a number, right? Ranging from general, how quickly do you converge to the right answer? What does this convergence look like qualitatively? Is it very stable? Is it more jagged over time? Beliefs oscillate. Or do I have a specific question in mind? What is the distribution of regret relative to always taking the best arm? So here, if you've had always taken the best arm, you have reward n times the highest mean reward. This is the cumulative sum of the mean rewards of the actions you actually took. And you might want to ask how much worse are the actions you actually took relative to the reward you could have gotten by always taking the best action. And to emphasize, in some sense, looking at regret is a very classical thing in this literature. There's a huge number of bounds showing kind of upper bounds with high probability on regret. But here, what I'm asking about is something different. Not what's an upper bound on regret, but what is kind of an instance-specific distributional result. Instance specifically, what is the distribution of regret going to look like? For example, if you have 5 arms and I give you specific choices from you, then I'm asking you to give me the distribution of Rn in this setup. So I'll just quickly pause here in case anyone has any questions about the high-level picture. Also, if any of you are able to put your camera on, that's very nice. So then I can at least see some people. One of the difficulties in this Zoom seminar is that sometimes it's hard to know who's here or if people understand or don't understand. So.
Yeah, I have a question.
All right.
If you have more arms, what change can I expect for the distribution?
That's a great question. So I'm gonna so what I'm gonna do here is first, so the point of this talk is gonna be to figure out a distributional kind of a diffusion approximation for what sequential experiments do. So then you can read off the distribution of regret from there. You can use this result with a small number of arms or with a large number of arms, and then compare. So you can do that. Now, how is this regret going to change qualitatively with the number of arms? In case of upper bounds, there we know the answer. Say, how do upper bounds scale with the number of arms? That's well understood. How are kind of fine-grained distribution properties of the distribution of regret going to change with the number of arms? That I can't tell you. I don't have a general result to, other than that you'll be able to use the machinery developed in this talk to kind of compute the distribution in any example you're interested in.
Okay,
and
I have another one.
yeah.
Can I think of these arms approximately or conceptually like degrees of freedom?
So there's the difference between this setup and kind of a traditional regression-based setup where you have when it's typical to consider degrees of freedom, is that here you actually control exploration. And essentially, if I have 5 arms and I play the second arm, I only observe an outcome for the second arm. I don't observe outcomes for the other arms. So essentially, there is this explore-exploit trade-off where if kind of you think arm 5 is a bad arm, then you never explore it, or you never kind of draw samples from arm 5, but then that means you don't learn more from it. So the trade-off here is different than usually when degrees of freedom are considered. The analyst doesn't consider the data collection process. The degrees of freedom are just a measure of the stability of a fitting procedure given kind of a stable data collection procedure.
Okay.
Right, any more questions at this point? Okay, keep going then. So anyways, just as a warm-up for kind of what would a good distributional result look like for sequential experiments, let's consider a very familiar example, and this is on understanding distribution for the sample mean. This is, of course, a very well-known example, right? If you have n samples, and if there were no adaptivity, that is that just in each draw you pull the same arm and observe an outcome from it, then we know that the empirical average minus the true population mean, if you scale it up by root n, this has a normal limit with variance corresponding to the variance of the sampling distribution. This is a very good, this is kind of course, an asymptotic limit theorem, but this is often also a very good finite sample approximation for the behavior of the sample mean. And for finite n, and kind of something you learn in applied statistics calls is that for many problems of interest, this kind of Gaussian limit theorem pretty much tells you what statistical methods are going to work and why, and gives you very helpful guidance on what you should do in practice. So this is good. So how does this relate to sequential experiments? You might think, well, for the average, we know what to do. Just take the sample size to infinity, and you can read out guarantees from that. So if a sequential experiment, let's just do the same thing. Let's push the sample size to infinity and see what happens. And of course, there are classical results on this. One of the most celebrated papers on this is from Lyon Robbins, who is one of the first papers on this stuff, and they showed that if you fix a reward distribution and you push sample size to infinity, then the expected regret, which roughly captures kind of how many mistakes you made before learning what's going on, they show that the expected regret scales like log n. So as you collect n samples, at some point the regret starts climbing very slowly. So this is kind of a very optimistic result as to the large sample behavior of sequential experiments. But on the other hand, the Lyon-Robbins result, the Lyon-Robbins result assumes that you fixed reward distributions and send the sample size to infinity. At the other hand, you might start by fixing sample size and then choosing the reward distribution to kind of make it as hard as possible given the sample size. And here you get lower bounds, these are to our et al., showing that for any sample size n, you can build some reward distribution for which regret is lower bounded by some constant times root n. So there's some tension here, right? For estimating a sample mean, just taking n to infinity, it gave you asymptotics, but not just that, it gave you this Gaussian limit that was a very robust finite sample approximation, or reasonably robust. Whereas here, when you take n to infinity, you get this log n scaling, which is just kind of a completely different picture of the difficulty of the problem as sample size gets large than what you'd get from taking kind of worst case finite sample bounds, right? Obviously, log n is not root n, and this matters in practice, right? If you have a sample size of 100,000, should you expect regret to be on the order of 5 or on the order of 300? Right? So anyways, here n goes to infinity. The Lyon-Robbins result gives us considerable insight into the nature of the sequential learning problem, but it doesn't give us an approximation theorem in the sense of the kind of traditional central limit theorem for the sample mean. So this gives you a natural question: what went wrong? Is it that kind of taking limits for sequential experiments is just not useful, or maybe should we have just taken a different limit? Right. Okay, I guess I've already told you my take now what the answer to this is. And here, this talk is about kind of a diffusion limit, and the claim is that if you consider a diffusion limit for sequential experiments instead of a classical just take n to infinity limit without changing anything else, then you're going to end up with a much more useful approximation result in finite that can help you get a picture of what's going on in finite samples. And so the way we're going to get this diffusion specifically is that, okay, we're going to consider a sequence of learning problems indexed by the time horizon n, or the sample size, but for each n, we're not going to leave the reward distribution fixed. Rather, we're also going to scale the reward distributions. And the way we're going to scale them is that the reward you're going to get from the k arm and the nth problem is going to be mu k, that's kind of your scale-free mean reward, divided by root n. So what this is saying is that as we push n to infinity, as we push the time horizon to infinity, we're making the problem harder. We're kind of changing the gaps between the arm rewards by downscaling them by 1 over root n. And so what this is going to mean is that even in very large problems, you're still going to have genuine uncertainty about which arm is best, because, right, if the difference between the rewards of each arm is on the order of 1 over root n, and you were to run a randomized trial, kind of uniformly randomized over the full time horizon, then you still couldn't perfectly tell which arm is best using the full amount of data. And just to be clear, I'm going to scale the mean rewards down by 1 over root n, but I'm not going to modulate the variances. The variances are going to be constant order. So this is going to mean that the difficulty of the problem is fixed as you increase the sample size. So this is the diffusion scaling. In this work, we started thinking about this diffusion scaling based on connections to the heavy traffic approximation from queuing theory, where kind of there's a similar intuition that kind of pushing the sample size to 0 here is it mathematically behaves a lot like pushing utilization to 1 in a queuing system, and then using that limit for kind of approximation. It also, of course, in statistics is closely related to local asymptotic normality theory, where you also kind of consider limits of experiments as the sample size shrinks as the effect size shrinks as the sample size gets large. So I already mentioned that kind of in this diffusion scaling, what this allows us is that as the sample size gets large, the problem is neither impossible nor trivial. It remains statistically interesting. And what you also get is that the regret you get under the diffusion scaling matches this order 1 over root n regret you got from these lower bounds from Auer et al. And in fact, to establish these lower bounds, they essentially do so along a sequence that looks like the ones we prove a diffusion limit for here. So anyways, this is the setting. Now I should tell you, give you a little bit more details about what we actually do. So at a high level, my goal is to do limit theory for sequential experiments in a way that kind of the limit doesn't just give you a scaling thing, but also gives you get a distributional limit that can be deployed as an approximation in finite sample. So that's the goal. Now I just need to tell you which kinds of sequential experiments am I going to run that give you these diffusion limits, and how do these relate to the diffusion scaling. So anyways, first on what kind of experiments am I going to run? In the interest of generality, I'm going to talk about everything for a little bit in the context of what we call sequentially randomized Markov experiments. So what a sequentially randomized Markov experiment is, it's really, like I said in the beginning, it's a randomized trial, but where the randomization probabilities can change over time. So like in a randomized trial, at each step I, the agent chooses has a probability vector pi I on what action to take, and then randomly draws the action they actually take based on these pi's. The only difference between a standard randomized trial is that these probabilities pi may change with time based on past history. They aren't fixed. And the way they can change that's where the Markovian comes in. We're going to assume that these pi i's can depend on two things. They can depend on the QKIs. This is the number of times you've pulled each arm up to time I. So you're allowed to take that into consideration. You're also allowed to consider the cumulative reward obtained from each arm up to time I, but nothing else. So we're going to assume that these pi i's don't depend on kind of intricate properties of the kind of whole cumulative sum process up to now. We're only going to assume that they depend on number of times you've drawn each arm up to now and the resulting rewards. And so kind of when you put these two assumptions together, what you find is that essentially a sequential randomized Markov experiment is defined in terms of this kind of psi function, which takes the Q and S object, which you're allowed to use, and maps that to a set of probabilities pi I that then determine your randomization probabilities. And we refer to the psi as a sampling function. So this is a sequentially randomized Markov experiment. It captures a lot of stuff you might be interested in practice. The thing I'm going to focus on here is Thompson sampling. It's kind of very classical approach to learning. I'm going to say more about it in a second. There's a question?
So, yes, cumulative, does it mean that there is memory here?
Yes, right. So we're running, the point of the sequential experimentation setup is that you're running a randomized trial, but kind of you see people in order, and you can learn from past observations and use that to choose which actions you take in the future. So what this setup assumes is that you're not going to deterministically pick one action or another based on kind of past stuff, but what you are allowed to do is based on what you observed in the past, tilt your actions towards more promising arms. For example, one simple thing that's allowed in this setup is what we call this kind of tempered greedy sampling. So for each arm, remember SK is your cumulative rewards. QK is the number of times you've pulled each arm. So SK over QK, that's the kind of apparent sample mean for the K arm. And so one thing we allow you to do is to look at SK divided by QK plus C. This is regularization, and just kind of pick arms depending on this current cumulative reward. Does that make sense?
Yeah, but I thought that Markov doesn't use memory.
Well, I mean, what is Markov? the meaning of Markov here is that so if you think of your state space as its Q and S variables, then kind of you only depend on your current state of Q and S. You're not looking at past history of rewards other than as they're expressed through the current number of draws and cumulative rewards.
Okay.
Yeah, so this isn't going to be kind of a finite state space Markov chain, right? Q and S are going to diverge, right, as the sample size gets large. In the end, we're going to want this kind of thing to converge to something like that looks like a Brownian motion. So it's kind of Markov in that kind of sense. I'm sorry, these slides keep once it's moving, despite my not clicking on them. Any more questions at this point? All right, great. And yeah, thanks for the questions. It's always much nicer to speak when there are questions than when they are not. So anyways, so that's a sequentially randomized Markov experiment. We're going to want to study those. We're going to want to study sequentially randomized Markov experiments under a diffusion asymptotic regime, that is where sample sizes get weaker as n gets larger. And now in order to kind of link these two together, we still are going to need one assumption on kind of how these sampling functions psi that underlie the sequentially randomized Markov experiment relate to the sample size n. And what we're going to assume is the following, that essentially psi n is the sampling function in the nth system, and we're going to assume that it respects the diffusion scaling as follows. So for some kind of scaled number of draws q and scaled rewards s, in the nth system, if you observe nq draws and get reward root n times s, then this converges to some limiting sampling function psi of qs. We're going to say that a sequence of sampling functions that satisfies this is convergent, and really this just means that the sampling function kind of is aligned with the limiting regime we're considering. Was there another question? Yes. Itamar? I can't hear you. I think you may be on mute.
Somebody. Anyway, so you use diffusion even at the very beginning, at the title, and I understand you use it in the sense of you're going to use diffusion results to develop your model, but in the end you said you will aim at Brownian motion. So what I'm looking, and Brownian motion is clearly a diffusion type. So what I'm missing is some connection between or interpretation of the sequential experiments in terms of physical diffusion, which is spread of something. Am I clear?
Yeah, so I mean, I guess maybe at this point it's helpful. So the main result is going to be that sequential experiments, right? These are things people run under these assumptions. That is that we have a sequence of problems that obey the diffusion scaling, and that we have consider sequentially randomized Markov experiments with convergent sampling functions. Then under these properties, the sampling paths of the sequential experiment, the sample paths of the sequential experiment are gonna follow the diffusion limit.
Okay.
And
okay,
so
this is
specifically,
good.
this is if you scale the kind of cumulative number of draws like this, so 1 over n scaling for the draws, 1 over root n scaling for the rewards, and then define these kind of continuum limits for q and s. Then the main result is that the sample paths of how many times you draw each arm and the cumulative rewards you have from each arm converge weakly to the solution to the following stochastic differential equation. Does this answer your question?
Yes. Thank you.
Thank you. Itamar, if you could mute, because it's otherwise we hear a background. That's why I had to mute you. Sorry, it's the background noise. Thank you.
Thanks.
Yeah.
All right,
So go ahead. Yeah. Thank you.
Okay. Thanks. So this is the first result, right? Just that kind of by taking the scaling. So now we're going to scale time to between 0 and 1, and then go along. Then you get this kind of diffusion representation of what the sequential experiment does. One thing also, just very quickly, we also have a representation of the diffusion limit in terms of this kind of essentially random ODE. So we first kind of get a random draw from W. It's a standard Brownian motion in RK. And then we show that kind of, you can think of the sample paths as of S and Q as being solutions to this ODE with this random component W. So this is kind of another representation of the diffusion. Anyways, I don't have that much time left, so I'm going to go quickly now and just talk about, okay. So we talked about sequential experiments. We talked about how kind of sequential experiments let you change adaptive randomization probabilities over time. If you just do kind of a classical limit where you fix the problems and n to infinity, then you can prove that you get kind of log n regret upper bounds, but you don't get distributional results. And actually the log n is kind of at odds with kind of worst case lower bounds on the order root n if you pick the sampling problem adversarially in terms of your sample size. So these are some challenges. And here what we did instead was we considered asymptotics with sequential experiments, but where we kind of downscale effect sizes as the sample size gets large. And here it turns out that the whole system converges weakly to an interesting limit, and this limit can be characterized as a solution to a stochastic differential equation. So now the claim is that the stochastic differential equation is not just interesting as a limit object, it's interesting as a kind of approximation tool that you could use to just study qualitative properties of sequential experiments. And to kind of see how this plays out, I'm now going to consider possibly the simplest sequential experiment you could ever look at. This is potentially something of a toy example, but a lot of interesting aspects of sequential experiments already play out here. And the idea is that this is a one-arm experiment. So your kind of agent isn't choosing between a number of different arms with unknown rewards. There's only one arm, and they can either pull the arm, in which case they get reward mu, where mu is unknown, or they can do nothing and receive a known reward of 0. And the question is, should they pull the arm or not, or when should they stop pulling the arm? And we're going to assume a diffusion regime where this kind of reward mu gets downscaled by 1 over root n. And in this regime, we're going to consider Thompson sampling, which is, if you're familiar with this literature, it's very widely used. Essentially, what we're going to do is we're going to assume that the agent is Bayesian, and at every time point, they start with a prior from mu. Every time point, they update the posterior, and then they choose to draw the probability that they draw from this reward distribution at the ith time point matches their belief at the time I that mu is positive. So the only remaining choice here is, okay, we're going to be Bayesian in this sense, is that we need to choose which prior to use. And so this nu n here is going to be the prior variance. If you pick kind of a very small prior variance, this is going to kind of act as regularization, force the agent to collect more data before it becomes sure that the arm is either bigger or smaller than 0, or if you let this prior variance be more diffuse, then you kind of more quickly can react to data. So two things you could do is you could either pick this prior variance on the order of 1 over n to match the diffusion scaling. And in this case, our results immediately imply that the diffusion limit for Thompson sampling has the following form. Or another thing you could do is essentially pick a prior that doesn't respect the diffusion scaling. That essentially, for example, you could just pick prior variance 1 regardless of sample size. So then kind of if you pick a constant order prior and you send the sample size to infinity, then in the limit, the prior is just not going to do anything and it's going to wash out in large samples. This might seem like a strange regime to consider here, but it's actually matches a setting that's largely considered in the theory literature on Thompson sampling. These papers that prove kind of robust upper bounds for Thompson sampling. So it's also something we wanted to look at here, and we're going to call this the undersmoothed regime. When you look at this, you get some difficulties regarding regularity conditions, which is using the general diffusion result I showed earlier. But kind of once you deal with these, you still get kind of the following diffusion limit in the undersmoothed regime. So okay, this is the diffusion limit for Thompson sampling. Here's a picture showing that, in fact, this diffusion limit is very accurate in capturing the finite sample behavior of Thompson sampling. But so now the question is, what can we do with this diffusion limit? And I think two questions that are immediate is first, we had to pick this prior for Thompson sampling, right? This new n. Obviously, a good choice of prior is going to give you an experiment that behaves a lot better than one with a poor choice of prior. So one thing you might hope to get out of this diffusion limit is some guidance on kind of what makes for a good choice of prior in Thompson sampling. Other questions you might ask is something about the evolution of sample paths. We have these kind of beliefs, pi I, about at time step I, did you believe that mu was bigger than 0 or not? And you might want to ask how jagged these beliefs are. Do they evolve smoothly or not? So let's see what this looks like. So the first thing here, what I'm showing is the regret of Thompson sampling in terms of the scaled reward mu. So here, kind of, if I say mu equals 5, that means in the horizon n problem, the reward is 5 divided by root n. I plotted the regret. So this is kind of the excess loss you incur from pulling the arms you actually incur versus kind of doing the right thing from the start. I plotted the regret for Thompson sampling for a number of different of prior variance nu, ranging from, in black, I showed c equals 0. This is the one where you kind of use a constant order amount of regularization that washes out in the diffusion limit, versus in different hues of red, you see the regret you get from kind of choosing some kind of non-trivial choices of regularization that don't wash out in the limit. And what you see here is something that was very surprising to me, is that especially when mu is negative, that is when you kind of, the arm you're pulling is actually bad and you want to stop pulling it. You want to notice that it's bad and they want to stop pulling it. When this arm is negative, it's essentially instance optimal to always use a diffuse prior. Kind of using any amount of regularization is only going to hurt you. This was surprising to me. I thought that kind of regularization would help here, but kind of from the diffusion limit, we see that this is not true. And actually, kind of using a diffusion limit, you can prove more. Essentially, when you consider kind of very strong effects, that is, when your reward distribution is like mu over Rudin for very large values of mu, then if you use kind of this C equals 0 scaling, that is, you use a prior variance that's so weak that it washes out, it's like using an improper prior, then as the effect size gets stronger, the problem gets easier, and you can check that regret is controlled not quite on the order of 1 over mu, but almost, right? It's controlled as 1 over any exponent of mu for beta, strictly less than 1. On the other hand, if you use C greater than 0, that is, if you use regularization that remains large, even remains non-trivial, even as the sample size gets large, then what we show is that when mu is large and negative, then actually your regret diverges as opposed to going to 0, like it should when you use undersmoothing. And when regret is large and positive, when mu is large and positive, regret still doesn't go to 0. So this is really this kind of sharp separation that shows that you might have thought regularization was good, but in the previous picture, I showed that kind of in finite sample, it's almost instance optimal to use an improper prior. And as you push samples that make sample sizes, effect sizes large, this dichotomy only gets accentuated. And the difference between using undersmoothing versus kind of non-trivial smoothing is the difference between getting vanishing regret on the diffusion scale versus kind of getting a lot of regret on the diffusion scale. So this is a first observation. Another one is, okay, you might think that, okay, undersmoothing using C equals 0, essentially using an improper prior, gives you low regret, so that's good. So now you might think that kind of in the C equals 0 regime, other good things should happen. Like maybe Thompson sampling should be very stable and right, have all these kind of nice properties you would expect out of a good statistical procedure. But that's actually not going to be true. What's going to be true is that in this setting with an improper prior, you're going to get low regret. But, sorry, I don't know why this is just, my slides are, okay. You don't just get, you get low regret, but the way you get there is using very, very unstable sample paths. So here you see over time, going from 0 to 1, you see kind of in different colors, different realizations of this experiment. And you see these beliefs, they kind of oscillate wildly at the beginning of time before stabilizing as time moves on. And when you turn this into a formal result, what you get is that actually, kind of regardless of the sample size, if you use C equals 0, that is, if you use this kind of scaling prior choice with good regret properties, then with very high probability, at some point in time, you're going to be absolutely convinced that the arm is good. And at some other point in time, you're going to be absolutely convinced that the arm is bad. And yet, eventually, you're going to recover and get low regret. There's a question?
Well, clarification, which is probably trivial, but not to me. And this is, can you tell me the connection between the sample path and the sequential experiments? Because this could help to understand the surprise and the regularization, and also the last point that you made, which, okay, maybe I lost it. Anyway.
So so we're running a sequential. Sorry, I'm going to put you on mute just while I respond, because otherwise I hear a lot of echo from kind of when I speak through the system. But so the sequential experiment is at each time point you have an agent. In our for Thompson sampling, the agent maintains beliefs about whether this kind of unknown mu is positive or negative. So at each time point, you have a belief. Based on that belief, you choose whether to draw an action or not, and then you update your beliefs. So what are the sample paths? Kind of over time, after I time steps, you'll have QI is the number of times you've pulled the arm so far. SI is the cumulative reward from doing so, and pi is your belief that, given the information collected in the first time steps, mu is positive. So this is a sequential experiment. The main result of the paper is that the sample paths of this thing are captured by the diffusion. And
so what is unstable path in this explanation?
So what I'm showing here is the evolution of these pi i's. That is, given the information about the, so here t is I over n. It's a kind of scaled sample point. So given the information collected up to, say, time t equals 0.1, what is your belief that mu is positive? And you see this belief kind of oscillates wildly at the beginning of time before kind of stabilizing potentially as t gets large. So this is what the instability is. The instability comes from just your beliefs about whether mu is positive or negative. It's not like in a proper Bayesian learning problem, you'd imagine that you have some belief. You start uncertain about whether mu is positive or not. So you start at 0.5, and then slowly and smoothly you kind of converge to either believing that mu is positive or not. And here that doesn't happen at all. You kind of are like, I'm sure mu is positive, I'm sure mu is negative, I'm sure mu is positive, I'm sure mu is negative. Over time, I eventually converge and get low regret, but I did so in kind of a very unstable way. Does that make sense?
Yeah, now I need to connect it to use surprise and to understand the answer to the surprise, if there is an answer. Because you were surprised by these two curves of scaled regret that had something to me like singularity or cusp, and on the right side you had a simple, nice, smooth sigmoid. But the point of the cusp or the singularity was at 0 mu, and the turning of the sigmoid, you know, from going up to going to saturation, was also at 0 mu. So, and that was the surprise, no?
So okay, here's a similar plot for the kind of showing regret for the two-arm case. So now it's not just mu that's unknown; it's their two arms, and regret goes as a function of arm gap. So here, the reason there's zero regret at 0 is this is just mechanistic, right? If there's no effect size, then whatever you do doesn't matter. So there's no regret. And this line, this dotted line shown here, this is kind of mechanistically the worst regret you could get by kind of always taking this is the regret you get in a randomized trial, essentially, if you just kind of never tried to adapt to your beliefs. So you always had regret kind of 0.5 times the arm gap. And so here you maybe see this phenomenon even more strikingly. I'm considering I see problems with a kind of scaled arm gap between 0 and 20 divided by root n again. And here kind of this shows the regret you get for different choices of regularization parameter ranging from c equals 0 to something larger. And here you see that kind of taking c equals 0 is essentially again instance-wise optimal. That is kind of regardless of the effect size, you're essentially better off using no regularization. And again, here what I mean is, again, what does regularization mean? It's your prior on how strong the effect is to start with. So let's say the true arm gap is 4. I could imagine that it would be a good idea to use Thompson sampling with prior variance set to like 16, so prior standard deviation set to 4. But then on this picture, maybe this line here in orange denotes this one here denotes the regret you'd get from using prior variance 16, so kind of picking a prior variance that actually is in line with the amount of signal you have here. Whereas when the effect size is 4, here's the regret you get from kind of picking the wrong prior, completely diffuse prior, and just running with that, and you get lower regret. So this is kind of the surprise, is that even though Thompson sampling looks like a Bayesian algorithm, choosing a prior in line with kind of the true effect size isn't what's going to work here. You're better off just using a diffuse prior. And second, that kind of using a diffuse prior is essentially, regardless of what the true state of nature is, using a diffuse prior is essentially going to give you lower regret than using any non-trivial prior with Thompson sampling. So this is the surprise.
Okay, fine.
But I think I'm pretty much out of time, so I'm just gonna skip some last points, and just kind of all I'll say here is that sequential experiments are widely used in practice, but kind of, and there's been some amount of limit theory for sequential experiments. But one limitation of this is that usually there's been a focus on worst case upper bounds, not on exact distributional results. And here what we showed is that kind of by considering a diffusion limit instead of the classical limit regime, you get more. You don't just get upper bounds, you get a sharp, you get convergence to a diffusion. And this diffusion can give you insights about the finite sample properties of sequential experiments also. So anyways, that's all I had for today. Thanks a lot.
Thank you very much, Stefan. Is there any question from?
Yes. Yes, there is. And this is beautiful study that I'm learning very many new concepts and approach. Now the question is, when I design experiment, is there some information I can draw from the subject matter of the experiment and merge it in this beautiful result?
That's very interesting, right? You would, because with Thompson sampling, you'd think that kind of one very natural way to merge information about kind of subject matter and the design of the experiment would be via the choice of prior used in Thompson sampling. And essentially, when I started working on this project, that's where I thought we were going to go. We were going to kind of give you guidance on how to do this. But then, somewhat unintuitively, it turns out that kind of, regardless of what you believe about the effect size distributions, you're best off using a diffuse prior. So there's not much to say there. Now, of course, I think where there would be much more to do is if you think that there are many arms, but you're kind of willing to link the rewards you get from different arms using some kind of model to kind of lower the dimensionality of the problem, or if you have that kind of further structure on the problem, then you'd be able to kind of, this result would be able to accommodate that kind of structure and would kind of give you lower regret, faster convergence. So I think that would be a very helpful way of using subject matter knowledge to get better behavior here.
Thank you, Itamar, and thank you, Stefan, for the answer. Any other question from anybody else? So I think, yeah, we would like to thank you for this beautiful presentation. I just have, if you don't mind, a very quick question, and I think it's kind of related to Itamar. Would it be, I mean, you work in this machine learning area, and would it be possible to have some explanatory variables that basically narrow down these options that you were talking about? So like exogenous information that you have?
So, yeah, so they're sorry, it's kind of, I can't go through these slides very fast. So in the second part of the talk, I talked about Thompson sampling, which is kind of this very stylized, in this kind of very stylized setting, where we were kind of just considering each arm on its own. But what the framework for doing this using sequentially randomized Markov experiments, this is kind of quite a bit more general. Let me get there. Here. So essentially, this sampling function psi here could do a lot of things. It could kind of exploit modeling information, other covariate information about the arms to kind of direct these randomization probabilities. And this would be kind of a plug-in point for kind of doing much more sophisticated things here also. But I should say in many applications areas also, even if they're large scale ones, often people are interested in running sequential experiments. There are 5 arms. They don't have really much strong prior other than that kind of these arms are going to have different rewards and they want to find the best one. So that is kind of in the machine learning community also, this kind of sequential experiments where just kind of each arm stands on its own is a widely considered one.
Yeah, thank you. Any other question from the audience? Otherwise, we will. Okay, so Jimmy, do you have a question? I believe that you can unmute. Yeah.
Hi, Stefan. Thank you for the great presentation. A lot to digest. One question. So here with this, you can identify average treatment effects, and can you extend this to heterogeneity in treatment effects for each arm?
That's a great question. One would imagine one should be able to do that. That's not something we've considered yet. So then, yeah, I think one should be able to do this. So kind of you want to kind of do you have a contextual bandit problem. Treatment effects vary with covariates. You want the diffusion characterization for that. I think that would be very interesting. And this would be kind of a natural direction to go from here.
Yeah, I think that connects with what Dolores was trying to ask, if there is a way to include all the information that one might have, especially here, for example, in Denmark, we have a lot of registered data and information about subjects, right? Anyway, but yeah, that was it.
Yeah, that'd be a nice direction to go, but that's kind of beyond the results we presented here, because essentially you'd have to. Here we only have like, depending on essentially what you wanted, if you want to have continuous actions or only continuous covariate space, it would require more or less extensions to the theory, but it doesn't. Yeah.
Awesome.
It's not quite easy.
Thank you.
Thank you, Jimmy. Is there any other question? Otherwise, I think we will thank Stefan for giving such an insightful presentation. We have enjoyed it very much, and you know that this will go to our YouTube channels. And for the audience, I would like to remind you that this is the last seminar of these 6 months that we have been together, and now we decided to return in September, so we will see you if you would like to join us on the 20th of September, but of course we will make some announcements on Twitter and also to the mailing list. We will be back with Coralia Curtis from the University of Oxford. Thank you so much, have a great summer, and see you after that. Bye-bye.
Thanks a lot.